Welcome to the Journey Shake Cam. Please do the 2 warm-up questions to the best of your ability, and we'll discuss them in a moment. In number 1, the first thing I have to ask myself, is this a weak acid or a strong acid? Well, I know it's an acid because it begins with hydrogen, and acids begin with hydrogen except for water. Well, it's not one of the 7 strong acids, and therefore it must be a weak acid. It's acetic acid, and I am given an original concentration of 0.22 molar. And so that is my initial value, and I have no dissociation initially. Then I have the change. Well, some of it will dissociate. I don't know how much, so I will assign it an X. Whatever dissociates has to come from this original amount. And I will get X of the hydronium and X of the acetate. It is a 1-to-1 relationship. And then at equilibrium, I bring these values down. And I get 0.22 molar minus X and X and X. Now I'm going to write out the equilibrium expression. It is just a very good habit because as we move to higher levels, we need to establish those basic habits so that the problem solving is easier. Well, it's the products, which is my hydronium ion times my acetate ion divided by my reactant, which is my acetic acid. And I do not include the water because it is a pure liquid. Now I'm going to substitute in the values from my ice chart. Initial, change, equilibrium. Well, I have X of the hydronium and X of the acetate. That makes for X squared. And I'm going to divide it by the 0.22, but I will not include this X value because I am going to assume that it is less than 5% dissociated, the 5% rule. And therefore, I'm going to use the 0.22 molar equals 1.8 times 10 to the minus 5th. And we will be given the Kas and the Kbs for the weak acids and weak bases. Then I solve for my X value. 0.22 times 1.8 exponent negative 5 equals square root. And I come out with X is equal to 1.9899 times 10 to the minus 3rd. Now this stands for the hydronium ion as well as the acetate ion, but because I want the pH, I need to know the hydronium ion. I'm going to follow through and round this to the hundredths place, and therefore I get 1.99 times 10 to the minus 3rd molar hydronium ions. And I'm going to clean this up a little bit so we are not confused as to what's going on here. And then I know that the pH is equal to the negative log of the hydrogen ion. pH is equal to minus the log of the hydronium ion. And that's what I was looking for. And these brackets mean molarity. And when I take the log of this number, I get 2.7011. Again, I'm going to round to the hundredths place, and my pH is equal to 2.70. Now I'm going to double check that I could follow the 5% rule, as well as the question asks for the percent ionization. Well, I take the amount that was dissociated, which is 1.99 times 10 to the minus 3rd, divided by my original amount, 0.22 molar, times 100. And I get 0.9045. And percents and atomic mass units are always taken to the tens place. And therefore, I have 0.9% that is dissociated and easily below the 5% rule. And that's how you do number 1. In number 2, I have a weak base. Remember, we have to make sure that it is a weak base before we go through this process. If it was not a weak base, then I could just go ahead and take the log of this to get the pOH. But I can't do that because this is a weak base. Ammonia is one of our most common weak bases. Now I'm given 0.35 molar of the ammonia solution, and I have nothing to begin with initially. Then the change is that some of it will dissociate. I don't know how much, so I assign it an X. Then I am going to say that it's going to be less than 5% dissociated, so I don't need to worry about any quadratic equation. Then I write my equilibrium expression for the weak base. And it is my products over my reactant. And because our coefficients are all 1, I don't need to worry about any exponents. Then I substitute, and I get x squared over my 0.35. And when I solve this, I find out that my x value is equal to 2.5099 times 10 to the minus 3. Then I round to the hundreds place. Therefore, the 9 rounds to 0 up. And x equals 2.51 times 10 to the minus 3rd. And here's a critical point. It's the molarity of my hydroxide ion. Right here, this is my x value. And when I take the log of this number, I get a POH. POH is minus the log of the hydroxide ion concentration. And therefore, when I take the log of this number, I get a POH is equal to 2.60. And then I know that my pH plus my POH is equal to 14. And therefore, I subtract this number from 14. And I get my pH is equal to 11.40. Now I must also find the dissociation percentage here, and I take the amount that was dissociated, my 2.51 times 10 to the negative 3rd, divided by my original amount that I had, which was 0.35 times 100. And when I do this, I see that I get 0.7% dissociated. Again, we're safe. We can use the 5% rule. It's less than 5% dissociated, and therefore we're okay of not subtracting it and not using the quadratic equation. And that's how you do number 2. Titration is a very important process that we do in the lab in chemistry. And it is a quantitative way to determine the concentration of a solution of an acid and a base. This is an acid-base titration. And we are going to use the equation where the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. Well, we're going to know that the molarity of the acid is 0.1 molar. And we will know that we have 10 milliliters of it, and that would be 0.01 liters. Because 10 milliliters, I change it to liters, and therefore there are 1,000 milliliters in 1 liter. And this gives me the 0.01 liters. I need to find the first day we're going to standardize the base. And it's sodium hydroxide, but we don't know the concentration. So we're going to do a titration where we have a burette that has the solution in it of the base, and we will drop by drop determine when it turns pink. And because this is a strong acid and a strong base, it will turn pink when the pH is 7. And when the hydrogen is equal to the hydroxide, we will get this color change. And when we figure out this number of how many milliliters it takes to get that pink color, we will be able to determine the concentration of the base that we have. And we call that standardizing the base. We use a known value to determine the unknown value. Then the second day, we are going to determine the molecular weight of an unknown acid. And we'll weigh it out, so we'll get the mass, and then we'll figure out the moles from our titration, and then we get the molecular weight. I'm sure it'll make more sense to you when we get to the lab, but I'm really excited, so please write up that lab procedure for tomorrow, and we'll get started on it then. I can't wait to see you tomorrow. Bye.